Welcome to another exciting episode of E301. So today we're going to talk about capacitor transient analysis. Move on to sharing the screen. So here we go. And we're over to the writing desk. All right, so capacitor transient analysis, learning objectives. We're going to calculate capacitor voltage and current as a function of time. So last time we talked about it in steady state. This is what happens when we're not in steady state DC, but we still are sort of in DC. So calculate capacitor energy stored before, during, and after a transient capacitor event. So we'll figure that stuff out. Now, start off with discussion of steady state. So a capacitor in steady state looks like an open circuit. Okay. In the circuit below, for example, presuming the circuit has been in the present state for a while, it reaches a voltage of whatever the source is when no more current flows. Okay. In this state, we pretend the capacitor is an open circuit because there's no current. So there's no current, that means we've got an open circuit. Now, what happens when the switch is not in steady state? So we've got the circuit shown below where the switch is not in either position 1 or position 2, and the capacitor is fully discharged, so it's got an initial voltage of 0. Switch is moved to position 1, what happens? All right, so before it's in position 1, we've got a voltage source of 100 volts, right? And that is going to a switch that is not connected. And we've got 1 k ohm and a capacitor, okay? So when it's like that, we're gonna assume, we're gonna stick down here a little ground for ourselves, and we're gonna say, all right, where are the nodes? So these are our nodes, okay? Now this position, so all of those are nodes. Now, at this position, we've got 0 volts, all right? At this position, we've got 100 volts. We've got an open circuit here, so there's no current flowing. We have no idea what the voltage drop is across that. But we do know that this capacitor has 0 volts across it before time t equals 0, which means that there's 0 volts across that, and there's 0 volts there. And what's the current through this resistor? Well, the current's 0 because there's nothing going through there. So we've got 0 volts here, which means we've got 100 volts across that open. Now, what happens immediately after time t equals 0? Okay, so now we've got 100 volts there. We've got our closed switch. We've got a resistor that is 1 k ohm. We've got our capacitor, and that's ground, right? So the capacitor, we know that this here, that is at 0 volts because that's ground. We know that up here, oh, it keeps going across, goes all the way across like that. All of that is at 100 volts, right? But what we also know is that VC is still equal to 0 volts. Why? The capacitor can't change voltage that fast. It doesn't change voltage unless there's a current flowing to it. Okay, so that means that this node is also at 0 volts. Well, now there's 100 volts and 0 volts across this resistor. All right, so what happens is all of a sudden we induce 100 volts across that resistor. That means that now we're going to get a current. So as soon as the switch moves to position 1, there's a drop across the resistor, and the current jumps instantaneously. Okay, so this leads to a first order differential equation that we aren't going to have you solve, but that's okay. We have the answer, and it's the general equation for a capacitor transient. So we were talking last time about capacitors and inductors. We moved down here to transient analysis. And we've got this equation. So VC of t is V final plus V initial minus V final, e to the negative t over tau. Okay, so the general equation is V final plus V initial minus V final, e to the minus t over RC. because tau, as it says right above it, is equal to RC. So that's that tau. It correlates right directly to there. Okay. So V initial in our case was 0 volts. So that's why we have that line there. You're going to make sure you draw that line so that you know what it was before. V final is 100 volts in our case. Okay. So RE up above, up there, that is 100 volts. Okay. With that known, we've got VC of T is equal to V final, which is 100 volts, plus the initial, 0 volts, minus 100 volts, E, oh, couldn't see, all right, there it is, E to the minus T over RC, okay? We can simplify that to say it's 100 volts times 1 minus E to the minus T over RC. So that's how, and this is how the voltage drawing looks. So at time t equals 0, when it transfers, all of a sudden it starts to change. So that's where the discontinuity is. Discontinuous. Okay. Up here, when it finally gets close, that's still continuous. We haven't changed anything. It's just sitting. It's decaying towards our value. Now, this is why we have a discontinuity. So we come in at a current of 0 amps, okay? Now you can figure out what all this is by saying IC of T is equal to C dVc dt, okay? Now, if we do the algebra, if we do the calculus on that and then figure out the algebra, we'll see C negative 1 over RC times VI minus VF e to the minus t over RC. Okay. Well, solving that further, we get 1 over R is V final minus V initial e to the minus t over RC. Okay. In our case, V final was 100, V initial was 0. So for our particular case, IC of T is equal to 100 volts over R e to the minus t over RC. But that's only valid after time t equals 0, right? Because before then it was 0. So that's the way we can figure that one out. All right. So that's the equations. Now, next thought we have is about the time constant. Okay. So what is the time constant? The time constant from the capacitor charging equation, we saw in here, we saw that we have that T and RC, right? So that T is in seconds. RC, well, what would that be in? So if we have, so the time constant is the rate at which a capacitor charges depending on R and C. It's called the time constant. It's denoted by T equals R. So it's the resistance seen by the capacitor. Okay, and this is why, and then you multiply by C. So seen by the capacitor. So what does that mean? That's RTH with the capacitor as the load. Okay, so the Thevenin equivalent is useful for figuring out what happens with the time constant. So it's RTH. Now, R times C, let's think about that. So R is equal to V over I, and C is equal to Q over V. So if we multiply, and I is equal to Q over T. So if we multiply, and we take that I and substitute in there, we get R times C. Okay, so R is equal to V over Q times T, and C is Q over V. The Q's cancel out, the V's cancel out, and we end up with time. So that's how we end up with seconds. We can rewrite the charging equation. So this shows VC of T is equal to V final plus V initial minus V final e to the minus t over tau. Okay. Now, exponential function's argument has to be unitless, so tau is in seconds. Plotting the voltage versus t, noting increments of tau on the time axis. Okay, so we've got 1 tau, 2 tau, 3 tau, 4 tau. After 5 tau, we're at 99.3%. So we're at less than 1% from the final value. For engineers, that's close enough. Okay, so we can presume that the charging transient is over after 5 time constants. And this is something that's not on the equation sheet, but we assume that T of steady state is equal to 5 tau. Okay, so in order to reach steady state, we wait 5 time constants, right? And it doesn't matter, and so that's for the charging. And it's not going to matter for the charging or the discharging. So now we're going to continue with that circuit that we were discussing before. Now we're going to say, all right, it's been in position 1 for a long time. So what's the voltage across the capacitor? All right, it was initially fully charged and acting like an open circuit. Okay, so now it's in position 1, and now what we're going to do is we're going to move it to position 2. Okay, moving it to position 2, we've got, so we start off before time t equals 0, we've got 100 volts there, and we've got our switch closed. The resistor is 1 k ohm. We've got our capacitor, right? And this has the C, and it has plus minus 100 volts. Okay, if that has 100 volts, right? This is ground. This is at 0 volts. That's at 100 volts. That node's at 100 volts. This node is at 100 volts. So if that's at 100 volts and that's at 100 volts, there's no voltage drop across that resistor. So I equals 0 amps, right? Now, what happens after time t equals 0? Well, we switch this switch, we move the switch from connected to 1, now it's connected to 2. And what it's going to look like is it goes directly to the ground, okay? Now we've got 1 k ohm. This is ground, and now ground goes all the way around. So that is 0 volts there, and this node is at 100 volts, right? Because that's the capacitor at 100 volts. Right now, this resistor has 100 volts across it, and we were originally defining our current is going that way. But which way do we think it's going to go? It's actually, the current's going to turn around. It's going to discharge out that way, right? Because this is going to be the high side. That's the low side. So this is the discharge equation. The voltage across the capacitor can't change instantaneously, but when the switch moves, the current instantaneously jumps, moves over to there, right? So the voltages and currents are going to change exponentially with time. Now this time it's V final equals 0 volts, because at the end of all this, there's no source. V initial was 100 volts, okay? Because once it's just going to discharge until there's nothing left. So VC of t is equal to V final plus V initial minus V final e to the minus t over tau. In our case, so we've got the E coming in on the left there. What's that at? That's at 100 volts. So our VC of t is going to be equal to 0 plus 100 volts minus 0 volts e to the minus t over tau, right? Okay, which then becomes 100 volts e to the minus t over tau. For the current, IC of t is going to be equal to V final minus V initial over R, e to the minus t over tau. And we already said what V final and V initial were. So we've got IC of t is equal to negative 100 volts divided by the 1 k ohm, e to the minus t to the minus t over tau. Because the V final is 0, V initial is at 100. So, as with the charging case, the transient can be considered to last for 5 time constants. Okay? Time constant tau is given by RTHC. So tau equals RTHC. So T steady state is equal to 5 RTHC. Remember, it's RTH. All right. So now we're going to look at this and we're going to say, all right, in the circuit below, the switch was shut for a long time and opens at time t equals 0. Determine the equation for VC of t. So this is something similar to what you'll see. All right. Now this capacitor is in parallel with there. It says, all right, the switch was shut for a long time. So we're going to redraw this. Okay. We're going to redraw it for before, and we're going to redraw it for after. Okay. So before, switch was shut for a long time. Right. So that means that we've got our source there, which is 24 volts. The switch is shut. We've got 3 k ohms. Okay. And we've got here, what's this one? That's 9 k ohms. Okay. And our capacitor is outside of it, right? So that's an open circuit. The voltage across this, so that's essentially, that's one node. That's a second node, and we'll say ground is there. And this is 24 volts, okay? Goes all the way over. Yep, goes all the way over. So 24 volts, this is at 0 volts, but we've got, there's no current going that way, all right? After, we've got, so the switch opens. What's that mean? Well, if the switch is open, this source is no longer in the circuit, and this 3 k ohm is not impacting what's going on with the capacitor. So we've got 9 k ohms. Okay, and this one is VC of t. So after. Okay, so this is what it looks like after. We've got this node, and for the after case, we're going to find RTH. Find RTH for the final circuit. Okay, so RTH for the final circuit. When we find RTH, we short out all the sources, but there's an open here. So if we put, this is our load right there, all right? So we pretend like this is an open, we've got a source where the load is supposed to be, the only thing that it confronts. So RTH is equal to 9 k ohms. All right. Now tau is equal to RTHC. RTH being 9 k ohms. C is 100 microfarads. So we get 900 milliseconds. Okay. Now we look for V initial. Well, V initial is in the before drawing. We've got, that's the voltage across the 9 k ohms, right? So V initial is equal to the 9 k ohms divided by, because it's a voltage divider, 9k plus 3k times 24. Okay, so that's 9k plus 3k is 12. 24 divided by 12 is 2. 2 times 9 is, so we've got 18 volts. Okay, V final. Well, in V final, there's no source over here, so V final is 0 volts. Now I write the equation. VC of t is equal to V final plus V initial minus V final, e to the minus t over tau. So VC of t equals 0 volts plus 18 volts minus 0 volts, e to the minus t over 900 milliseconds. Or if we want to consolidate it, we end up with 18 volts, e to the minus t over 900 milliseconds. Now remember, you need to include the units for both of those. And that is, oh, there it is. That is the answer for that one. All right. And with that, I'm going to stop so you guys can learn more from everybody else.